Okay, we're going to discuss bond dissociation energy, which is the energy required to break a chemical bond. So if we imagine the H2 molecule, which is two hydrogen atoms connected by a single bond, if we would like to break this molecule into two single hydrogen atoms, that's going to require the input of energy. So that means, in a sense, that this process is going to be endothermic. On the opposite hand, if we take these two hydrogen atoms and we connect them in a new chemical bond, that's going to release energy. So this process, in a sense, is exothermic. And this is always going to be the case, that the breaking of chemical bonds requires energy, whereas the formation of chemical bonds releases energy. And we can measure this energy, the energy required to break chemical bonds, and this has been done several times in a variety of molecules. And you can actually take the average energy for various chemical bonds and tabulate them. So for example, that's what's shown in this particular chart here for single bonds. If you take the average of a bunch of, say, carbon-hydrogen bonds, you find that it takes 413 kilojoules of energy to break a carbon-hydrogen bond. How do I know that's carbon and hydrogen? I look here at the chart at the intersection of carbon and hydrogen, and this will tell me the average energy it takes to break a bond where a carbon atom is connected to a hydrogen atom. And you can see, you can get a wide variety of information by looking at this particular chart. In terms of multiple bonds, double and triple bonds, you can look through this particular chart here, and you can see, for example, that on average, if you're going to try to break a carbon-carbon double bond, that's going to require 610 kilojoules of energy. And now if we look at the carbon-carbon triple bond, that takes even more energy, 836 kilojoules per mole of these bonds. Let's see, what's a carbon-carbon single bond look like? That looks like 346 for a carbon-carbon single bond. So as we go from a single, 346, to a double, 610, to a triple bond, 836, we see that as bond order increases, bond energy also increases. So let's check this out for the hydrogen-hydrogen bond. Let's see, that's going to be 436 kilojoules per mole. So for the breaking of this bond, we're going to need the input of 436 kilojoules. And then if these two atoms combine, that's going to release 436 kilojoules. And the information in this chart can be used to estimate. It's not going to be perfect because they're average energies, but this information can be used to estimate the enthalpy of a particular chemical reaction. Let's try it. Let's do this for, let's say, the decomposition of hydrogen peroxide. So H2O2 goes to 2H2O plus O2. Now to do this, we're going to first need to draw Lewis structures for all reactants and all products. So if you end up doing that for hydrogen peroxide, you end up getting a Lewis structure that looks like this for hydrogen peroxide. And then of course for water, you're going to get a Lewis structure that looks like this. And then for oxygen, we're also going to get a Lewis structure that's an oxygen-oxygen double bond in the oxygen molecule. Now we're going to need to recognize that in the chemical reaction there's 2 moles of hydrogen peroxide. So we're going to go ahead and add in a second molecule of hydrogen peroxide. And we're also forming 2 moles of water, so we better add in another water molecule. And then what we do, we recognize that if a chemical reaction is taking place, in a sense, you're going to end up breaking all of the bonds in the reactants and form all of the bonds in the products. So because of that, if we're going to use bond dissociation energies, we're going to break all of these bonds. So this is going to require the input of energy. The energy is going to be positive. So I'm going to have to break this bond, this bond, this bond, this bond, this bond, and this bond. We're going to have to break all of those. And we can look up how much energy it's going to take to break those bonds in this particular chart. So if we look, I see I have 1, 2, 3, 4 OH bonds. That's going to need the input energy, so I'm going to take a positive 4 times whatever this OH energy is that I'll look up in this chart. OH, that's going to be 463 kilojoules. So I'll write that in there, 4 times 463. And then I'm also going to have to break 2 OO single bonds. So let's look in our chart. An OO single bond, that's 146 kilojoules each. So there's 2 times 146, and all of these units are kilojoules. And these are positive because I'm breaking the bonds, that's endothermic. Now on the other side, we're going to make all of these bonds. So on this side, this is going to be exothermic. All of these are going to be negative. So it looks like I have 1, 2, 3, 4 OH bonds. We already showed over here that the OH bond is 463. Just to remind you, OH single bond on average is 463 kilojoules. So we're going to have a negative 4 times 463. And we're also going to make an OO double bond. It's exothermic, it's going to release energy, so I'm going to put a negative OO double bond. I got to go over here to the multiple bonds chart. OO is 497. So we're going to subtract just one of those, 497. Okay, now we can add everything up. 4 times 463, that's 1852 positive, plus 2 times 146. I'm just going to go ahead and add in 146 twice. Yep, so it's positive 2144. That's what it requires to break all of these bonds. So I write that in up here on the top. Positive 2144 kilojoules. That's the sum of all this to break all of these bonds. Now over here on this side, let's calculate how much energy is released when all of these bonds are formed. So it's going to be 4 times 463. And we're going to make that negative. And then we're going to subtract 497 for this. So it's going to be a minus 2349 kilojoules. So now we take the sum of these two, so this minus this. Or I can take 2349 and add 2144. Negative 205 kilojoules. So using average bond dissociation energies, we have calculated that we would estimate that 205 kilojoules are going to be released for every 2 moles of hydrogen peroxide that undergoes this process. Well, for every mole, let's just divide it by 2. So we're going to divide that by 2. It's going to be negative 103, we'll call it, kilojoules for every mole of hydrogen peroxide that goes through this particular process. And that's actually quite close to the known enthalpy for this particular reaction. The known enthalpy for this particular reaction ends up being minus 98 kilojoules for every mole of hydrogen peroxide that is decomposed. That's not too bad. We can use these average bond dissociation energies to estimate the enthalpy for chemical reactions.